questions?
Okay. Let's start the conversation. Our next speaker is Yotam Hendel from Bernstein University, and he will tell us about one of the versions of Harish-Chandra's regularity theorem and singularities in orbital computation.
Okay, so thank you very much, and it's a very big honor to give a talk in this conference with so many distinguished speakers and distinguished listeners. As Anna mentioned, I'm going to talk about the quantitative version of Harish-Chandra's regularity theorem and about singularities of representations. And this is joint work with Itai Glaser, who sits there. Wait, if I can not that one. And also with Julia Gordon from UBC. And I guess just to start things up with some settings, then I'm going to take some finite extension of QP to be F and G to be the F points of some connected reductive group G. And I'm going to let rep G be the category of smooth representations of finite length of G. And by smooth, just as usual, I mean that the stabilizer of each vector in V is open in G. Now, I'm going to denote by irg the collection of irreducible representations of G. And while I have these settings, I just want to mention that most of the results that I'm going to discuss also hold in the real case, except for maybe one theorem which I will mention that does not hold in the real case, but just for simplicity, I'm going to focus on these p-adic settings just because I don't want to repeat every sentence twice. Now, given a finite length representation, then I can consider its distributional character. So usually a character is just a function, but here if I have some Schwarz function, f on S of G, then I can define it just as written on the board. And the idea is that after I average this operator pi g with respect to some nice locally constant compactly supported function, I get an operator between finite dimensional vector spaces, and this operator has a trace, so this is meaningful. And as you see, a priori, this is a distribution on G, but due to the theorem of Harish-Chandra, if we have an irreducible representation pi, then actually this character is given by a locally integrable function, so a locally summable function. And in addition, this function is locally constant on a dense open set, so the set of regular semi-simple elements. And furthermore, if I take this function and multiply it by a certain function called the well discriminant to the power of 1/2, then this is furthermore locally bounded. So a priori, this is some distribution, you don't know anything about it. But actually, this is a very well-behaved distribution, namely it is given as an integration with respect to some L1 function. Okay, so the well discriminant, this will be quite important for us later. And I guess I will define it a bit later on the Lie algebra. But what will be something that will be important to us is that it is an ad invariant. This is some polynomial living on your group, so some polynomial function. And well, we said that this theta pi is given as a locally summable function, but actually, if you consider this well discriminant a bit more closely, then you see that this integral. So if I take some small ball b around some point, and I consider the integral of the well discriminant absolute value to the power of negative 1/2 raised to some number s, then this is integrable for s slightly larger than 1. Now, what does this tell me? So this tells me that theta pi is better than locally summable. It's better than L1, namely it is L of 1 plus s for some small s, and this really follows very, I'm just going to write it out so it's clear. So I'm just claiming I can do something very naive, and if I have such an integral, will be some small open ball, and I know that theta pi absolute value times dg to the power 1/2, this is bounded, and I can just multiply and divide by the same factor. So I have an S here, S here. And I know this guy is bounded. Therefore, convergence of this integral as in the fact on the board really says that my character is better than locally L1. So we can ask by how much more is it more sample, and we can capture it using a definition. And this is the integrability exponent of the representation. And I define it, and maybe I want to record this. I define epsilon star of pi at some point x to be the largest number such that theta pi is locally LF1 plus S integrable around x, and this is all happening in G. Any questions?
You said largest number, but you wrote superroom and you meant superroom, yes?
Yes. Okay. And well, if I can, so this is a local invariant, so I can consider it on small neighborhoods, but I can also define it globally. Just take the worst epsilon over all points. So epsilon star of pi just be the infimum of epsilon star pi at x as a vary over x. And this is an a singularity invariant of representations. Namely, it takes larger values for more singular representations. Also, well, it's a number, as you see. That's what I want to say. I think I want to keep the definition up. So if you consider some very simple examples, so for example, if pi is the trivial representation, the character is just going to be constant, and therefore epsilon is infinity. And this is in some sense the most singular representation. And this also makes sense if you say consider, okay, we will see that if you consider the local character expansion, then really it only has one orbit in its trivial orbit in its local character expansion. In addition, by analyzing, by not so hard considerations, you can also see that epsilon star only takes finitely many values. So this is something discrete. And for GLN, if epsilon star of pi attains the minimal value, then it is generic in the sense that it has a non-degenerate Whittaker model. Actually, for GLN, actually, it's even on. Any questions so far? Very good. Please stop me if you have any questions.
Actually, I have a question.
Yeah.
Let's take the representation of the representation of GL4, you use from a character of GL2. What is the epsilon of that representation?
I don't know. If anybody has questions that don't require pen and paper. Okay. Yeah. Okay. So we have a new singularity invariant of representations. We want to calculate it. We want to see whether we can say something meaningful about it. Can we give some lower bound? And the question is, how can we actually do it? And the answer that comes into our help is the local character expansion. So let me recall this very briefly. So let me denote by G the Lie algebra of G, and let me denote by O of 0 the set of nilpotent orbits of G on its Lie algebra. Then, if I have a nilpotent orbit, as usual, it supports some invariant measure, and by theorem of Deligne-Rangarau, this measure extends to a measure on the Lie algebra. And I denote this nilpotent orbital integral by mu of O, and by mu hat its Fourier transform. And now the Harish-Chandra character expansion tells us that near identity, we can describe the character of an irreducible representation as a linear combination of Fourier transforms of nilpotent orbital integrals. So more precisely, I have some complex numbers only depending on the representation, and some neighborhood of identity in the Lie algebra, such that for every x in this small neighborhood, theta pi of the exponent of x is given by this linear combination. And the upshot of that to me is that if I want to study integrability and singularities of the character on the left-hand side around identity, I can study each of these Fourier transforms and get results back on my character. Now, noted by similar version of Harish-Chandra regularities theorem, it also follows that mu hats are also locally integrable. So this actually makes sense. They're locally L1, and you can also define epsilon star of mu hat in the same way that I have defined for representation. So just ask what is the largest number S such that this mu hat is locally L of 1 plus S integrable. So this implies that really if I want to study the singularity invariants of representations, I can focus on the singularity invariants or integrability exponents of these Fourier transforms. Okay, any questions so far? No, seems good. Okay, so in general, these mu hats can be complicated, but one class of which is relatively nice behaved is the class of stable Richardson orbits. So let me recall this briefly. I say that an nilpotent orbit is Richardson if there exists some parabolic subalgebra in the Lie algebra such that this orbit intersects its radical in an open set. And they say that an orbit is stable if it is just an orbit of G underline of F bar on the F bar points of the Lie algebra. Now, not that actually this is called, so a stable orbit is not actually a G orbit, it is a union of finitely many G orbits. And when I consider the Fourier, when I consider the nilpotent orbital integral associated to a stable orbit, I just consider the sum of the corresponding nilpotent orbital integrals. Okay. So some examples, the regular orbit and subregular orbits are always Richardson, but well, stability is a bit of a tougher point, even in SL2R, the regular orbit is already not stable. And a point which would be very useful to us is that in GLN there happens some magic, and every orbit is both stable and Richardson. And this will be a case where we can carry on very nice analysis, and I will get to it later. Okay, so I can start discussing some results. So the first thing that we can do is that for stable Richardson orbits, we can relate the integrability exponent of mu hat to a certain singularity invariant called the low canonical threshold. So the low canonical threshold is, and this will be low canonical threshold of a certain also a kind of a well discriminant. So okay, so I'm just going to keep the slides here, and then I'm going to say something about them. Good, yeah. So okay, so what is low canonical threshold? What is this relative well discriminant? So low canonical threshold is a certain singularity invariant. Comes from bidirectional geometry. Yeah.
The regular orbit is not
Stable? No. Yeah.
Didn't you mention that?
I said it is not stable in SL2R, not stable. Yeah, you have this cone and it splits into. Yeah. It's the nicest, easiest example. So thank you. Okay, so what is this low canonical threshold? This low canonical threshold is a certain singularity invariant coming from bidirectional geometry. It measures how far is a hypersurface from being low canonical, which is a certain class of singularities. And it can be defined in the following concrete way. So really it measures integrability of your function to the power of negative s. Measures what is the supreme over all s larger than 0, such that this function is locally integrable around x. And the second object appearing in this formula is the relative well discriminant. So maybe let me define this very briefly. So if I have some Lie algebra, I can restrict it. If I have some Lie algebra, I can define the following thing, the following function on a torus. I take a torus, and then I, given just a value in this torus, I multiply alpha of t for all roots alpha in some absolute root system, and I get an expression, and I can now I can extend this function to a function defined on the entire Lie algebra by acting using conjugations and using continuity. So this gives rise to, this does give rise to some other invariant polynomial function. There is a more direct way to see this, but this is one way to introduce this function. But maybe. So there is a function called the well discriminant, and when you restrict it to the torus, it is just given by multiplication of these roots. And in a very simple example, so if you, for example, think about GLN, then you get a Vandermonde determinant of a Vandermonde matrix, so a Vandermonde determinant. Now I define, so just as a very simple example, I can take L to be GL2 plus GL2 sitting maybe inside GL4. So this will be L, and now when I consider this well discriminant of this Lie algebra, it will be the product of these elements of the roots in L, and I define the relative well discriminant DGL to simply be the quotient of these two expressions. So namely, I'm just not including the products, the roots living in L in my product. The point is that this relative well discriminant is also a polynomial function. It's a quotient, but just an honest polynomial. And the idea is that we can express the integrability of the Fourier transform of our nilpotent integral just as, twice the low canonical threshold of this relative well discriminant. And now, and this means that we can actually translate our problem to a problem in algebraic geometry. This is some polynomial. We are interested in its low canonical threshold. This is just, we want to understand its integrability. So if we know how to, for example, monomialize this function, we can solve this problem. Any questions? Okay. Good. Okay, and this is the last click I didn't commit, but yeah, the relative well discriminant is just this quotient of these two well discriminants. Yeah.
Is it the same as the first root of Bernstein Saturn or no?
Very good question. So if you have singularities which are worse than rational, the answer is yes. Other than this, then otherwise you need to clean out some root, and then it's true, and you have something called the minimal exponent, which measures what you, well, the first non-trivial root. More questions? Okay. Okay, cool. So we want to understand epsilon star of some representation. We know we will do this by saying something about epsilon star of nilpotent orbital integrals. So let me denote by h of g the Coxeter number of my root system. And the first, okay, I guess the second thing that we can show is that if I consider the integrability exponent of the nilpotent orbital integral associated to the regular stable orbit, then this has the same single. So this is twice the low canonical threshold of the relative Weyl discriminant with respect to the torus. So this is just the entire Weyl discriminant, because if I have a torus, then I don't exclude anything for my product. And the answer to this calculation, so this log canonical threshold is given by, well, twice the log canonical threshold is given by 2 over this Coxeter number. There is one assumption that I make in this theorem. Okay, so connected simple group, this is not a problem, but I do need F splitness, otherwise I just have an inequality. And just as a quick example, so this I want to keep. So in this case of GLN, this Coxeter number is just n, and therefore we get that this epsilon star of mu OST hat is 2 over n, and we will see that this is the worst, this is the smallest epsilon can be in this setting, so for GLN. So a conclusion.
This is for n is bigger or equal to, yes?
Yeah, I guess so. The n equals 1 case is a bit, well, epsilon is always infinity, right? If you have only character. Okay, so what can we get out of this? So if G is some F points of some connected reductive group with Lie algebra G, no further assumptions, and GK are the simple constituents of the commutator of G with itself. Then for any finite length representation that I choose, its integrability exponent is going to be bounded from below by 2 over the minimum over 2 over the Coxeter number. And you can note that this doesn't depend on the representation. This only depends on the group. So you fix some group, representations can't be less integrable than that. In particular, so just to spell this out, this means that if I have this pi in, say, simplicity energy, remember, then theta pi lies in L of 1 plus this minimum, so let's say epsilon by minus delta, and 0. So in the GLN case, every representation will lie in, say, L of 1 plus 2 over n minus delta, or actually delta out of it. So this is just translating verbatim what I said into writing. Now, in the case of GLN, all orbits are stable in Richardson, and we can actually explicate this integrability exponent and get some very nice numerical answers. So we get the following. So let O be some just some nilpotent orbit in GLN. And these are classified just by partitions of n. So you have your Jordan normal form. Let's assume that it has blocks of sizes nu1 all the way up to nu m. So now if O was the zero orbit, then this is not so interesting. Mu O hat will just be a constant function, and epsilon will be infinity. Otherwise, we can calculate the integrability exponent of mu O hat and get this following numerical expression. And we do this by calculating twice the F-log canonical threshold of the corresponding Weyl discriminant. Now I should say what is L in this picture. So if I have some O, nilpotent orbit is inside G, and let's say O mu, and we have this partition. It is a Richardson orbit, so there is some parabolic such that it intersects its radical in an open set. Let's assume this parabolic is P, so this is the Richardson parabolic associated to O. I can write it as L plus N, and this is the L appearing in this relative Weyl discriminant. And the connection between this new, so this, if I was, so now I'm in GLN, right? So this is all happening in GLN. And therefore this Levy L is also given as a product of some GLN case according to some partition of N. And the connection between this partition and the partition of the orbit is that they are conjugate. So I can take okay, actually let me return to this in maybe 2 minutes. But they're conjugate, so I'll just show an example soon. So one thing we do is we actually calculate all these integrability exponents of nilpotent orbital, Fourier transforms of nilpotent orbital integrals. Secondly, we show that epsilon star reverses the closure ordering. So if I have a small orbit living inside the closure of a bigger orbit, then the larger orbit is going to have smaller epsilon. So it's going to be, well, less singular if you wish. And okay. So let's see some examples.
This corollary you did by the computation, or you did there.
Yeah, so that's a very good point. This corollary, the second item is done using computation. In particular, if we have a non-GLN, in the non-GLN case, we think this should happen, but we don't know how to prove it. Because here all orbits are stable Richardson, so we have the formula for all orbits, and this expression is complicated, but we can still make sense of it. And also we have some Lie theoretic interpretation of this expression. But in the general case, then you have some non-Richardson orbits, and then you don't know what to do with it. Okay, so let's see some examples. As I think I've mentioned, if I have the regular orbit, it corresponds to this partition just one block, and the epsilon is 2 over n. If we have the subregular orbit, then it corresponds to this partition of n minus 1 and 1, and the epsilon of this guy is 2 over n minus 1, so this is subregular orbit. Yeah, said it. Now, you would think that only for the minimal orbit, the largest value of epsilon will be attained. This is, or I don't know, maybe not think, but one, yeah, that hope. But actually, any orbit corresponding to a maximal parabolic has epsilon equals to 1. But this doesn't, there probably isn't a much simpler expression for this expression above. If you just take n very large and you just pick randomly an orbit, it's going to be a mess. You're going to get some phase number. In particular, you see that, so for example, here this is 2 over n, this is 2 over n minus 1. You would hope that, if you consider some small examples, so maybe let me show. Okay. Allow.
you get one when you have two colors?
So, okay, so let me show you a picture because we're after lunch and I think picture is always a good idea. Okay. Okay, if I manage to scroll down. So this is our preprint, and in the preprint we have a very nice table. Where is the table? Here is the table. Okay, can you see something? So let me do maybe like this. Let me fold this. Okay. Okay, good. Don't allow. Okay, so this is the table for GL10. You can see all of the epsilons for these orbits. So you can see the regular orbit there on top. You can see the subregular before it. And there are errors. The errors are just a closure relation.
I'm ready when you are. What about the table for Glenn?
I'm sorry, not today, Glenn. So we have, you can see the regular orbit and then the subregular orbit. Now you can see that for many orbits, you just get epsilon to be 2 over the largest part of the partition. But this is something that really only happens in small cases. So we ran some calculations on like, using Python and I can try. Okay, we can see parts of it. Okay. So we did some calculations, and if you check all these orbits such that epsilon is not 2 over the largest part, then this is the majority when n is very large. Already for GL10, you can see that, okay, so these are all like 2 over the largest part, but already like this orbit corresponding to partition 6,4 has epsilon 13 over 41. And as you just look at this table, then you see that you also have some crazy numbers. Now, let me scroll down. So this is the bottom. So this is the trivial orbit. And here you can see all orbits corresponding to partitions of form 2 to the j, 1 to the complement. And all these orbits correspond to Richardson orbits with maximal with Richardson parabolic, which is a maximal parabolic. So for example, let me take 2 to the 4, 1 to the 4, like this orbit over here. So these are the Jordan blocks. If you want to see what is the corresponding Richardson parabolic, I can do the following thing. So I can draw the Young diagram. Any questions or comments?
Question. It always, you say that it's often 1 over the largest part, but often
2 over the largest part.
2 over.
Yeah, so for example, you can see that, well, you can just see 3 squared, 2 squared, and 2 over 3 is that.
So is it always better than that? Or?
Let's see. So 17 over 27 is seems worse than this, right?
So
2 over the largest part. What?
So it's always worse and sometimes equal.
It seems to be well.
Always better, loud, yes. Better than loud, yes.
So actually, well, it depends. Okay, so good question. It depends on your point of view because a generic representation has the lowest possible, or like the smallest possible epsilon, right? It's supported on the regular orbit, so it's 2 over n. But you consider a generic representation to be nice, right? It's a generic, not singular. The trivial, yeah, okay. So it depends on your point of view, whether on which side of a Fourier you are.
It's always larger than 2 over the largest part.
That's a good question. I don't know.
Smaller.
Always smaller.
I don't know. Here, in this specific example of 3 cubed, comma 1, it is smaller.
The largest part was 6 in that example. If you go up to the line with 6.
Yeah.
Let's see.
13 over 41 is small.
So it seems.
41.
Yeah, smaller than it could be smaller than 3, but the question is.
It's also,
It could.
it should be.
Seems to be smaller, yeah. But
So it's always smaller?
I don't know. Well, this is.
I don't know that one.
Smaller or equal than 1.
Okay, I don't.
You don't know.
Yeah, I don't know. You think it's always
smaller liquid than 2 over the largest part.
okay? Yeah, because okay, the large part is always appears. Okay, yeah. I think if you look, okay, let me comment on this in a second. Just to finish this, so to start with this orbit, you want to see what's the corresponding maximum parabolic. You just conjugate this. You get this parabolic. So 8. You should get some parabolic of size. So this is the parabolic figure. So this is this connection and the orbits, Richardson orbits with Richardson parabolic, which is maximal, correspond to these orbits with epsilon equals 1. Any more questions about this or about the picture?
So how do you get this formula?
Okay.
What is the meaning of the denominator and numerator?
Okay, great question. Let me get to this at the end when I sketch my the proof of this theorem. The quick answer is that we use some resolution of. Okay, I will get to it. There is not really a quick answer. And I'm just going to say one last thing, that I think that this if you take this minimum and if you take k to be, I think 1, then maybe you already get 2 over the largest part, right? I'm not sure. Okay, never mind. Just okay, I'm just commenting that maybe just from this formula you can see that epsilon is always smaller or equal than the 2 over the largest part, just by taking k to be 1 or something this form.
So if you do not GLN, but Richardson orbits, you also have some similar formula like this without numbers, but with
Yeah. So we get some formula involving some lead data, and for GLN we can actually explicate this to get this. So you take this formula from this lead data, you use you analyze it combinatorially, and then you get more questions. Yeah.
So there was a research formula for GLN for when epsilon is 1 greater, or when the character is L2. So does the part we have similar thing for other groups?
So that's a great question. I just want to mention that the character is always, well, you don't actually know whether it's L2. It's slightly less. It's slightly worse than L2 for sure, but right, because epsilon only measures like a pole, so you only know that you are integrable. This is if you're slightly below it, and the second.
So it's not L2, yes, it's almost L2, but it's not.
Yeah. So yeah, and
Sometimes it really isn't so and not better than L2. So it seems like it
I
does
don't
something.
think it can be.
Yeah, but it's never.
It's clever, but it does happen. It's necessary. It's not necessary.
okay, let's maybe continue in a second. But I just want to mention that again we get a formula for epsilon star of mu hat for any stable Richardson orbit in any Lie algebra. And now if you actually want to explicate this, this is some work, and in particular there are a lot of questions. So the answer is I don't know, but you can try and see for yourself. And okay, just to crunch everything that I've mentioned in this theorem, it follows that if I consider this epsilon of mu hat, it always lies between 2 over n, so the smallest possible value, and 1, and this is only discretely many values, so this is somehow the range that integrability can take. More questions? Okay. Good. So let's continue discussing the great case of GLN. And we talked about integrability exponents of Fourier transforms of orbital integrals. Now we want to say something about representations. So we have this result due to Morlaine-Waltz-Berger. And essentially it says that if we have an irreducible representation of a p-adic group, of GLNF, not of p-adic group, and we consider the local character expansion of the character of pi, then I have a unique maximal orbit appearing in this local character expansion with coefficient which is non-zero, And the closure of this orbit contains all other orbits appearing in the local character expansion. So saying that something about the wavefront set of this character. And using this theorem, we can pull back our results about integrability exponents of Fourier transforms of important orbital integrals to representations. And we can show that if we have any reducible representation of GLN F some p-adic field, and O max is this maximal orbit in the sense of the above theorem, and then the integrability exponent of pi, so of the character of pi at identity, is given precisely by this epsilon star of mu O max hat. And this is something we can calculate using this previous theorem, as you saw before. And okay, so all of these results they mentioned so far, they all work in the real settings. This specific theorem does not work in, or is not proven in the real settings, although we think it should be proven because there are some analogs of this theorem of Muglen and Watzberger. But other than this, the previous, so if I click back and go back to this theorem, so this also holds in the real settings, and also this lower bound also holds in the real settings, so there is no, this is some kind of a uniform treatment. It doesn't really matter because of the methods. And specifically for this result, in the p-adic case, the local character expansion is just a linear combination of some functions. In the real case, this is some asymptotic expansion, so it's a bit harder to work with. But we think also this theorem should have an analog in the real settings. Okay, any questions? If I continue. Okay. So what can we do this? We can give some interesting applications. Just checking if there's, oh, I'm good. So we can give some applications. So firstly, focusing on the p-adic case, we can show bounds on multiplicities of k-types occurring on multiplicities of irreducible representations in restrictions to open compacts. So if pi is any representation and of G, smooth pi representation of G, and K is an open compact subgroup, then if I take some number epsilon smaller than my epsilon star of pi, I have some constant depending on the representation pi, on the open compact K, and on epsilon, such that if I take any reducible representation of K, the multiplicity of this tau in the restriction of pi to K is smaller than this constant times the dimension of tau to the power of 1 minus 2 epsilon over 1 plus epsilon. And the idea in this kind of, the idea to get this kind of results is really using a non-commutative Fourier transform. So I know that if I have some function lying inside LP of something compact, then I know that f hat is going to lie inside LQ when 1 over P plus 1 over Q equals 1. And now if I take P to be just 1 plus epsilon, so you can calculate what Q, so if I take P to be 1 plus epsilon, so you can calculate what Q is, and I have to see what I wrote, because otherwise there is absolute no way to remember. And if you unravel these formulas, you can see that you can really get such bounds. And in the case of parabolic induction, we can actually calculate this even further. So firstly, because of the fact that the character of parabolic induction is the same as the Weyl discriminant to the power of 1/2, we can calculate its integrability exponent and get that this is just some Fourier transform of some nilpotent orbital integral. And again, you have this connection that I've explained before. So you have a parabolic with some partition, and then you have its Richardson orbit, which is obtained as the orbit corresponding to the conjugate partition. So this is this connection between lambda and nu. And here P lambda is just this parabolic induction from P lambda OF. OF is the ring of integers of F to GLN OF. So this is the first thing we can show. Secondly, if we take one and the previous theorem, we get the following bounds on multiplicities of irreducible representations appearing in this parabolic induction compact groups, and get the bounds as written. I think that's my question. Okay. Now, if we go to the Archimedean settings, then we can also get some bounds on multiplicities. And now I want to take some K to be compact and connected. Yeah.
The previous result, is it sharp? Or larger. So if epsilon is not smaller than epsilon star, then it will not be true. It's a different leaf.
A good question. Let me think for a moment. Yeah, okay, I'm not sure. I need to think about it.
And the corollary
exponent says it's not shallow.
Yes, yeah, whether this is sharp, well, I don't know.
Actually, the people can get a satisfying bound for all representations of all groups and all K terms.
Again, can you ask the question again?
But asking around, if you actually believe you can get a satisfying bound in this level of generality, because you work on all groups and all representations and all open compacts.
I mean the first theorem. The first theorem. So if just epsilon star equal to the rate of growth of this multiplicity.
I also would bet against it.
Actually, it's like saying if you have a function which is L1 plus epsilon, it's Fourier transform.
Yeah.
It belongs to some empty space. So
Yeah.
it's not open direction. But
The actual way to derive this is quite nice. Is in this sense just using this Hausdorff-Young inequality.
So it's one.
You apply for a transform, you see it's an LQ, and then you say, well, it's a sum of a lot of coefficients, so each coefficient should be smaller than something. Yeah, so yeah.
But there might be direction.
Okay.
but we expect it to be close.
Okay.
Probably not far.
Okay, but so I have 15 more minutes about.
15 more minutes.
Okay, good. Okay, so going to the real case, so again, K is some compact connected Lie group, and L is some Levy subgroup, meaning that it is a Levy of some complex group in which K is the maximal compact and intersected with K. Then the first thing we can do, we can calculate the integrability exponent of the character of L2 of K over L. And we can get some answer in Lie theoretic terms, very similar to the way we derive the theorem for GLN. And secondly, if we consider unitary groups, so let lambda be some partition of n with non-zero parts, and K to be the unitary group of size n, and L to be a product of smaller unitary groups of size Li, then epsilon star of L2 of UN modulo U lambda is precisely L, so the number of parts. Not mentioning random matrix here. And in addition, we get a result very close, very similar to what we got for the p-adic case. So again, using this Hausdorff-Young inequality, we get a bound on multiplicity of irreducible representations appearing in L2 of K over L. Okay, questions so far? Okay. So in the remaining couple of minutes, let me say something about the methods. at least about some of the methods. So recall, so we want to prove this kind of equality, and you have something sensible on the left-hand side and something maybe not so sensible on the right-hand side. And the way to do it is as follows. So recall that we are in this position of the algebra being GLN. We'll not use it until the very last step. And we know that by the first theorem that I've mentioned, we know this first inequality by the first theorem they mentioned. This mu hat equals twice the F-log canonical threshold of this relative well discriminant. And actually, to get this result, we can realize the Fourier transform of this nilpotent orbital integral as some kind of push-forward measure from some nice space. And then we have a result in some previous work which allows us to calculate epsilons of push-forward measures using the Jacobian of the relevant map. And in this case, the map is something like you start with some generalized Springer resolution, where P is the Richardson orbit, and then you can construct some kind of dual bundle such that the push forward. So if you construct a measure on this dual bundle and you push it forward, you get the Fourier transform, and this allows one to translate the integrability exponent of mu hat into the low canonical threshold of this relative well discriminant, because our theorem really tells us that this epsilon is given by the low canonical threshold of the Jacobian ideal of the corresponding map. So this is how we get this first equality. And recall that the low canonical threshold of DGL, well, the low canonical threshold of DGL was defined as the largest number such that this expression without the over 2 converges, but because I multiplied by 2, I need to divide by 2. So really, this is what I want to show. I want to show this equality. And all this should happen on a ball small enough contained in this Levy subalgebra L, because the DGL is a function on it. Okay, so I want to estimate this integral, and whenever I have an integral of a conjugate invariant function, the first thing I should do is use the well integration formula. And this well integration formula allows me to move and work on a torus instead of working on the entire Lie algebra. So I get a sum of a bunch of expressions of the form as on the board, as they vary over different tori, so over representatives of conjugacy classes of maximal F tori in L. And now I have this, each expression, each summand is of this form, and I can use some results of Harish-Chandra to get the following two things. So firstly, the maximal contribution to this big sum of finitely many expressions of this form will be obtained on the maximal F split torus. So again, we are working in GLN. I can assume it is a split, and this is what I do now. And secondly, by Harish-Chandra, this inner term is a unit around 0, so I don't have to worry about it. In other words, I can just worry about just this expression, integral of t dgl negative s over 2 dl to the power 1/2, and that's it. So this is, I have this something which is bounded. I don't know. This guy is unit near 0. So I need to take care of this integral, okay? And I need to take care of this integral on this maximally split torus. But now, if you remember the way I defined this relative well discriminant, this was a function such that when I restrict it to this maximal split torus, it's a product of these roots. And this is where I can switch to more or less to algebraic, to thinking in algebraic geometric terms. And each of these roots is actually hyperplane in this maximal split torus. And this function, this product, actually gives me a hyperplane arrangement. Now, hyperplane arrangements are things that, so let me see if I'm synced with my, yeah, okay. So yeah, so I can pass, and this delta G is just a product of all roots on T, and now both this delta G and delta L, they give me hyperplane arrangements, and these are things that people have studied for a very long time. In particular, people know how to monomialize them. There are some very explicit algorithms to do so, that give the degrees of the resulting polynomials in a rather explicit way. So this is what we do. We use some algorithm to resolve the singularities of this integrand and also of the Jacobian. And after we do that, we can interpret in linear theoretic terms, and some pages later, B is just some small ball in the F split torus around 0.
In the torus. The integration is
This is, yeah, this is on the torus, yeah. These functions only live on the torus. This is just a product of roots. So after we crunch things, we get this kind of expression. And so far, again, we only use the fact that G is F split. And specifically for GLN, we can make sense of this expression. So namely, we can show that it is piecewise monotone, and we can use this very nice structure of orbits using partitions. And using all, and okay, we can show that we can take this minimum over only certain Levy subalgebras. And okay, and by crunching this more, we get this expression that I showed. But the crucial part is really translating this into this language where translating this into hyperplane arrangements, then we can resolve singularities, we can give this interpretation, and this is something we next. So this is a sketch of proof, or at least a sketch of some of the proof, because there are some combinatorics and some Lie theory arguments that don't appear here. Any questions so far? Okay. So if not, these are questions, and also happy birthday to Joseph. So in the spirit of today, I've asked ChatGPT to draw a birthday poster also involving D modules and parallel sheaves and p-adic groups. And I just want to mention that when I asked ChatGPT, then he gave me this picture, and he mentioned that the D module is represented as a glowing floating scroll or book emitting ethereal light, symbolizing the depth of differential equations, algebraic structures. It went on. Also, the parallel sheaf is visualized as an intricate, translucent tapestry weaving through the scene, indicating complex topology. Okay, so it has some thoughts. But happy birthday, and thank you very much for listening.
Yeah, so I have a question. So you said that it is not clear in general that this number attached to a nilpotent orbit is monotonic with respect to the closure relation. But why cannot you have a kind of delta-like sequence going from bigger orbit to smaller one?
Okay.
To show that the function that you were interested in for smaller orbit is the kind of degeneration. So on bigger orbit you have invariant measure, but you can multiply it by a function, and then probably you would obtain kind of the same numbers.
Okay.
And then you kind of do the this accumulation measure around small orbit and show the inequality. So this have you tried something like that?
No, I'll be happy to hear about it more thoroughly, but you want to
large orbit to an orbital integral on the small orbit.
Yeah, to try to push all the measure towards the smaller orbit.
I think I know. Okay.
You're talking about,
Yeah, well, and then
Before you do-
look at
before
the
the
Fourier
Fourier
transform.
Okay.
Do it before Fourier transform.
Okay. So you say we do it before Fourier transform, kind of squeeze it to the boundary, if I
Yeah,
understand
yeah,
correctly?
squeeze the measure to the boundary.
No, we haven't tried that. So actually, the way we show this theorem for Richardson orbits is using some. Okay, we understand this structure well enough, like this function well enough, so we can conclude this. But yeah, we didn't try it in different approach. It's a good idea. It's a good question if this can work. And by the way, just to want to mention that already for the minimal orbit, this is an interesting question. So I think the minimal orbit should always have epsilon equals to 1 for any what that you choose. So this is already. It would be interesting to check this because it appears.
And I don't know what Richardson orbits are stable outside of the GLN.
Outside of GLN,
For classical.
for classical, so I'm not sure. So actually, the Richardsonness is the big problem. The stability, we can work with this because, well, there is a subtle point because when we consider this local character expansion, it is just a linear combination of things which are not necessarily positive, so there could be some cancellations. So the stability thing is an issue, but not such a big issue, so we didn't.
But other than stability, it doesn't really depend on the local key, right?
Yeah.
So for example, if you ask a question over C, the stability won't arrive.
Yeah. So there are a lot of things that we think should be true, but we still. So for example, we don't think there should be cancellations. If you have like a large orbit splitting into some smaller orbits, probably some argument, I don't know, on the way, some argument should show that they cannot cancel singularities, but okay, it may be checked.